So the next topic is angular momentum of a rigid body in case of rotation about a fixed axis. Okay, so we are going to have a rigid body which is rotating about a fixed axis. So let us represent it in a coordinate system. So this is my x-axis, this is my y-axis. Let's take this as x-axis, this is y-axis, and this is z-axis, and this is my rigid body, okay, which is rotating about this axis, let us say in this particular manner, with a certain angular velocity. Okay, so let us say that the mass of this rigid body is m, okay, and it is moving with an angular velocity of omega. Okay, and this angular velocity is along the z-axis. So this rigid body is made up of large number of elements. So let me consider one element. Okay, let us say that element has a mass of m. Okay, so let me consider that element over here. Okay, and this particular element has a mass of m. Okay, let us say that it is the ith element, so I will say in general this has a mass of mi. Okay, and definitely we know that every element in a rotational motion rotates about the axis with certain radius. Okay, so let us say that this is that radius which is r. Okay, I'll say it as a position vector of that ith particle or ith element about the origin. Okay, or since it is the ith particle, I will call it as Ri. So that is the position vector of this ith element about the origin. Okay, let us consider that the linear momentum of this particle, which is going to be tangential at this point, be pi. Let this be the linear momentum of that ith particle or ith element. Okay, so the angular momentum of this element will be given by what? So I have taken the position vector as Ri and the mass, okay, this will write separately for the element. Okay, for an element, okay, mass is mi, then position vector is Ri and the linear momentum is pi. Okay, so therefore the angular momentum of this element will be given by what? The angular momentum of this element about the axis of rotation, which will be represented as Li, will be, we know that it is given by Ri cross Pi. It is the cross product of Ri and Pi. So what is the direction of Ri? Ri is in this particular direction, Ri, okay, and this is Pi. So obviously radius is at 90 degrees to the tangent, so angle between Ri and Pi is 90 degrees. So apply the rule, take your right hand and curl your fingers from first vector to second vector, that is from Ri to Pi. You will see that the thumb is pointing on top. If you curl your fingers from Ri to Pi, you will see that your thumb is going to point on top, which is going to be the direction of Li vector, which is along the z-axis. Okay, that is the rule, right, to find out the direction of cross product. Okay, so I can write this as the magnitude of Ri cross Pi will be what? Ri Pi sine of theta, where theta is the angle between Ri and Pi. But theta in this case is 90 degrees. Theta in this case is 90 degrees, so it is going to be Ri Pi. Sine of 90 is going to be 1. Okay, but we have to mention the direction over here, and we just now saw according to the rule by curling the fingers of right hand from first vector to second vector, that is Ri to Pi, I got the direction of the Li along the z axis, positive z axis, so that I will represent it as k cap. Okay, so this is going to be the vector Li that I got over here. So I got Li vector is equal to Ri Pi into k cap. So now we know that the momentum, linear momentum, is given by mass into velocity. So if I consider the velocity of that ith element, mass of that ith element, that is going to give me the linear momentum of that ith element. Okay, so if I substitute it over here, it is going to be Ri into Mi into Pi, that is Vi into k cap. Okay, but we also know that V is going to be R into omega, that is Vi can be written as Ri into omega. Now omega I will not come over here. Why? Because the angular velocity for every particle of a rigid body remains constant. So all the particles will have same angular velocity, right? That is same as the angular velocity of that rigid body. So we can write this as Ri into omega itself. Omega I will not come. Okay, so let's put it over here. So what we will get? We will get Li is equal to Ri into Mi into Ri into omega into k cap. So Mi into Ri will be Ri square into omega into k cap is going to be Li. This is going to be, now see, what is going to be Mi Ri square? Okay, there is going to be this quantity we have already defined, that is moment of inertia. We have already defined it as moment of inertia, but before writing it as moment of inertia directly, let us generalize this statement for the entire rigid body. So this was the angular momentum of the ith element, of this single element. So if I want to find out the angular momentum of the entire rigid body, what I will have to do? I will have to take a vector addition of angular momentum of each and individual element. So total angular momentum of the rigid body will be equal to the angular momentum of the first particle plus angular momentum of the second particle plus of the third particle, so on, that of the nth particle. So vector sum of individual angular momentum will give me the total angular momentum, which I can write as summation I is equal to 1 to n Li vector. I'll go on adding them, right? So I can write this as the total angular momentum. Same way, this also I will just summate on both the sides. This I will take summation on both the sides. Summation I is equal to 1 to n Li, that is going to give me the total angular momentum. On the other side also, I is equal to 1 to n Mi Ri square into omega into k cap. So now summation of all the angular momentum is going to give me the total angular momentum of the rigid body, which will be equal to summation I is equal to 1 to n Mi Ri square. Now omega is same for all the I elements, right? So omega I will keep outside, k cap also I will keep outside. So now tell me, what is summation I is equal to 1 to n Mi Ri square? That is nothing but the moment of inertia of this rigid body, of this entire rigid body about the axis of rotation. You take Mi and you multiply Ri square to it, and you sum it for every particle of that body. You get the moment of inertia of that entire rigid body, right? And what is left over here? Omega into k cap is left. So I'll write over here, this is going to be I, that is summation I is equal to 1 to n mi ri square is nothing but the moment of inertia of a rigid body about the axis of rotation. Correct? So I get L is equal to I omega into k cap. But luckily, if you look, omega is also in the direction of k cap. Omega, that is angular velocity, is also in the direction of z axis, that is k cap. So I can write this omega into k cap is nothing but vector omega, which is also along the z axis, right? So L can be written as I into vector omega. So here I get the angular velocity in terms of the moment of inertia and the angular velocity of the body, of the rigid body. And remember that L and omega both are along, the direction is along the axis of rotation, that is z axis. This is going to be the direction of L and omega. So conservation of angular momentum, we know that angular momentum of a system remains constant if no external torque acts on it. This is the statement, we have already learned this. Okay, so using the expression we just now derived, we know that L is equal to I times omega. Now see, this is analogous to the relation of linear momentum, that is mass into velocity. Linear momentum is replaced by angular momentum. Mass is replaced by moment of inertia, and the linear velocity is replaced by angular velocity over here. That is the difference. So we know that this is the relation we have. So if I differentiate this particular relation, both sides with respect to t, okay, if we differentiate both sides with respect to t, I'll get dl by dt is equal to I is constant, okay, d omega by dt, okay, but or rather let's put it together, d by dt in the first step, I into omega. Okay, now dl by dt, we know very well that rate of change of angular momentum is nothing but the net torque acting on the body. Okay, so if we substitute it over here, we'll get net torque will be equal to d by dt of I omega. Okay, and if the net torque becomes equal to 0, that is the net external torque acting on the body is equal to 0, then we can say that d by dt of I omega is equal to 0. That means there is no change in I multiplied by omega, or I can say that I into omega is constant. Okay, so this is the law of conservation of angular momentum. That is, angular momentum of a body will remain constant, that is I omega is angular momentum, right? That is L. If you look over here, that is L is constant if the torque acting on the body, the external torque acting on the body is 0. This is what we can say. Next we are going to study about the rolling motion. So what do we mean by rolling motion? So the combination of rotational motion, so I'll write rotational motion plus translational motion gives us rolling motion. Now we have to note that this rotational motion should be without slipping, that the body which is rotating should not slip, okay, due to the lack of friction. Alright, so if we have a combination of rotational motion and translational motion, of a rigid body together, it is called as the rolling motion. So let us consider a spherical rigid body. We can consider a cylindrical body also having a radius r. Okay, let us say that this body is rolling over a horizontal surface. Let me say that omega is the angular velocity. Omega is the angular velocity of this rigid body, okay, about the axis of rotation. So axis of rotation is passing from the center over here where the center of mass is marked. So when this rigid body is going to roll over a smooth horizontal surface, it is going to have two kinds of motion simultaneously. Okay, number one, okay, the two types of motion are, number one, the rotational motion, as we discussed. One is going to be rotational motion, okay, about the center of mass, it is about the axis of rotation, and second is going to be the translational motion. Okay, the second is going to be the translational motion of the center of mass. Center of mass is going to move forward, right? As this body is going to roll, the center of mass is going to move forward in this direction over here, like this. Rather, all the points will move forward with a certain velocity, as well as there is going to be a rotational motion over here about this center of mass. So now this body will roll over the surface without slipping if the point of contact, let us say this point A over here is the point of contact. So if this point of contact is at rest at any instant, okay, with respect to the center of mass, then we can say that this body is going to roll forward without slipping. If this body is not at this, if this point of contact is not at rest, then this body will start slipping. So this body is going to roll without slipping only when this point of contact over here, that is point A, is going to be at rest with respect to center of mass. Okay, so the magnitude of velocity of a point at the outer surface of a spherical body will be equal to what? If I consider any point on the outer surface of the spherical body, for example B, the magnitude of its velocity will be given by what? Obviously its velocity will be given by omega, that is angular velocity multiplied by r. So this is going to be omega multiplied by r. For example, I consider point B. It is the point on the outer surface of this spherical body, right? So it is going to have certain velocity equal to v omega multiplied by r. Okay, what about the velocity of the center of mass? Now this center of mass is having a translational motion, it is moving forward, right? So velocity of center of mass over here is also going to be omega into r, that is velocity with which this body is moving forward is going to be equal to omega into r. Now how do we get this? For example, let us consider we have a horizontal surface, okay, and there is a body which is rolling on this horizontal surface. Okay, so now let us say this is the point with respect to the center of mass is over here. If this body is rolling in front, okay, by the time this body rolls in front, it reaches over here, the same body reaches over here. Let us say this point reaches over here after this distance is covered. This particular point, let us say point A, reaches over here. It is rolling this way, right? So it rolls such that the point A reaches over here. So let us say it has covered an angle of theta with respect to this point of contact. So from this point of contact, the angle covered by that point A during the rotation is theta. Okay, so how much will be this distance covered? Obviously, it's quite obvious that this particular arc length will be equal to this distance covered. Okay, now it doesn't look like over here in the figure. But obviously this particular arc length that has been traveled, that will be same as the distance covered over here, the horizontal distance covered over here. And how much is going to be the arc length? Supposing the radius of this wheel is r, then arc length is going to be, this arc length is going to be r, that is radius, multiplied by theta. Right? So this distance is going to be r multiplied by theta. So supposing this distance is covered in some time t, the distance is covered in some time t. Okay, so now this distance covered is r multiplied by theta. Let us say this distance is x cm, that is the distance covered by this center of mass. Obviously the center of mass has traveled a translational distance equal to this much, let us say x cm. So this xcm is equal to how much? R into theta. So on the both side I will divide by the time it takes travel that much distance. So xcm divided by t is going to give me velocity of this center of mass, linear velocity, which will be equal to r into theta upon that time will be what? The angle covered in certain time gives us the angular velocity of that body, which is omega, which we have taken as omega of this body. So this is how we get the linear velocity of that center of mass is r into omega. Okay, so this is how we get it. Alright, so this is the velocity with which the center of mass is moving forward. So if I want to find out the velocity of this point B, how much is going to be the velocity of point B? How can I find out? See, the velocity of point B at the top of spherical body, the topmost point, I want to find out its velocity with respect to center of mass. I want to find it with respect to center of mass. Center of mass. What is it going to be? It is going to be equal to, its velocity. Its velocity tangential is given by omega into r, and we are finding it with respect to center of mass. Now center of mass is already moving in the same direction with a velocity of how much? Center of mass is already moving with a velocity or equal to omega into r, and we are finding this velocity of point B with respect to center of mass, right? Center of mass is already in motion with a velocity of omega r, and point B is also moving with omega into r. So with respect to center of mass, I'll have to add the velocity of center of mass also. So velocity of point B is omega r plus with respect to center of mass means the center of mass is also moving with omega into r. So total velocity of point B with respect to center of mass will be 2 times omega into r. Okay, so thus in case of a spherical body, rolling over a horizontal surface, the velocity of the topmost point of the body is going to be maximum with respect to center of mass. The velocity of the point of contact will be 0 with respect to center of mass, and the velocity of center of mass itself is omega into r. Okay, so if you look, as you go above, the velocity of every point is going to go on increasing. Alright, so this is about. So the last part of the chapter is the kinetic energy of a rolling body. So let us consider a wheel rolling over a horizontal smooth surface without slipping. So this wheel has two kinds of motion. One is a rotational motion about an axis passing through its center. So there is an axis of rotation, that is the shaft or axle you can say. That is the axis of rotation about which this wheel is rotating. And secondly, there is a linear motion of the center of mass. The center of mass is moving forward in the horizontal direction. So let us say that this particular wheel moves forward with a speed of v, and it is rotating about an axis which is passing through its center with an angular velocity of omega, that is marked in the figure over here. Therefore, the total kinetic energy of a wheel over here is going to be an algebraic sum. Since the kinetic energy is going to be a scalar quantity, it is going to be an algebraic sum of the linear kinetic energy, or a translational kinetic energy we can call it, okay, of the motion of center of mass, and the rotational kinetic energy. So sum of linear kinetic energy or translational kinetic energy of the motion of center of mass and the rotational kinetic energy of the center of mass. So linear kinetic energy over here obviously will be given by half mv square, plus we know that the rotational kinetic energy is given by the formula half I into omega square, where I is going to be moment of inertia of this wheel and omega, as we know, is the angular velocity. So if r is the radius of the wheel over here, if r is the radius of the wheel, then we can say that linear velocity is given by r into omega, or from here we can say omega is v upon r. So this omega, which is equal to v upon r, I will substitute over here. So the total kinetic energy, let us say E, will be equal to half mv square plus half I. Instead of omega, I will put v upon r. So v square upon r square. Okay. So here what I will do is, on this side I will just multiply and divide by m. The rotational kinetic energy term I will multiply and divide by m, and I will take out half mv square common. So what I will get, 1 plus half is gone out, I will remain, v square into m is gone out, divided by r square will remain and m will remain. So m r square is going to remain over here. Okay. So now over here what we will do is, we know that I is equal to mr square. So I'll say since I, that is moment of inertia, is equal to mr square, okay, or rather since r we have taken is as the radius over here, okay, I won't take this as r, I will take the letter k, because the moment of inertia is mass of the body multiplied by radius of gyration square, right? So r I have taken as the radius of the wheel. So obviously radius of the wheel and radius of gyration won't be same. So I will take it as k over here, that is k is the radius of gyration. So I'll say where k is the radius of gyration of the body. So I will substitute in this formula over here. So E I will get is equal to half mv square into 1 plus, this is going to be I will be m k square upon m r square. So this m and m is going to cancel out. So we'll get k square upon r square. Okay, so this is the formula we get, total kinetic energy of a rolling body. So this covers the theory part of your chapter number 7, that is system of particles and rotational motion.